In the first part of this question, we are analyzing turning points. So to do that, let's make use of dy dx. So taking this, let's differentiate it to get dy dx. So differentiating ax gives me a, and differentiating this gives me a minus b over x minus 2 squared. And turning points, it is also places where stationary points occur. So stationary point, that will be when dy dx is equal to 0. Let's go for that. So we are going to be letting dy dx be equal to 0, which means that we will get a minus b over x minus 2 squared to be equal to 0. So b over x minus 2 squared, this is going to be equal to a, x minus 2 squared, this will be b over a. So x is going to be equal to 2 plus or minus square root of b over a, which means that we are expecting two possible x coordinates that will cause dy dx to be equal to 0. And the two possible x coordinates are 2 minus square root of b over a. The other one is 2 plus square root of b over a. But this comes with a condition. The condition is such that b over a must be a number that is positive, or else when you square root this number, you're going to get a complex number. So in order for b over a to be positive, there are two possible conditions. The first one will be when a and b are both positive. The second one will be when a and b are both negative. So that will be the two conditions that will cause the curve to have two stationary points. So let me code this down. So therefore, for the curve C to have two stationary points, or two turning points, to have two turning points. For this curve to have two turning points, the two conditions will be when a is bigger than 0 and b is bigger than 0. Or another possibility is when a is less than 0 and b is less than 0. In part 2, we are given that a is equal to b. If a is equal to b and they are non-zero constants, that will imply that both of them must be bigger than 0 or both of them must be less than 0. And according to what we have derived in part 1, this will be implying that the curve has two stationary points or two turning points. So what the question is asking for is the range of values that y can take. To explain to you what this question is asking for, let me try to sketch out a possible curve for you. So if let's say a is a positive number, so let's say a and b, they are both positive, then for this graph, we will have two asymptotes. We will have an obvious vertical asymptote. So let me do a quick sketch here. We'll have a vertical asymptote, and this is x is equal to 2. We will have an oblique asymptote, y is equal to ax. And since I'm assuming that a is bigger than 0, to just have a visualization of the graph, so we have an oblique asymptote that has a positive gradient, a. So we have this. So for the curve to have two turning points, the curve can potentially curve, the graph can potentially curve this way. Here. So it has two turning points. And the range of values that y can take will actually depends on the y coordinate of this minimum point. So this will be the range of values that y can take, and it will depend on the y coordinate of this maximum point. So this will be the set of values that y can take. So we are going to try get the y coordinate of these two turning points. And in the previous part, in part 1, we have actually found the x coordinate of these 2 points. Because when we let dy dx be equal to 0, when dy dx is equal to 0, we have found that x is equal to 2 plus or minus square root of b over a. And since a is equal to b in this case, we will have a 2 plus or minus square root of a over a, which means that we will have 2 plus or minus square root of 1, which is 1. So the two possible x coordinates will be 2 minus 1 or 2 plus 1. So we have two possible x coordinates, and they will give me the corresponding y coordinates, which will then subsequently help me to determine the range of values that y can take. So when x is equal to 1, let's find what is the corresponding y coordinate. That will be a times 1 plus b, I'm going to just replace it by a. So a over 1 minus 2. This is equal to 0. And when x is equal to 3, then y is equal to a times 3 plus a over 3 minus 2. And this is equal to 4a, which means that if the y coordinate of this point is 4a and the y coordinate of this point is 0, then the set of values that y can take will be y to be less than or equal to 0 or y to be bigger or equal to 4a. But there is still one more catch, because a can be either positive or negative, which means that we need to code our answer based on two cases. That means we will have two possible range of values that y can take. The first is when a is a positive number. So let me just code it down here. If a is a positive number, then we will be expecting something that is like this. Then the range of values that y can take will be, if you are to look at this graph, it will be when y is less than or equal to 0 or when y is bigger or equal to 4a. That is if a is bigger than 0. If a is less than 0, can you imagine what is the range of values that y can take? The range of values that y can take. This time it is going to be when y is less than or equal to 4a or when y is bigger or equal to 0. Let me very quickly explain to you this before I end this part. Because now we are analyzing the case where a is less than 0, which means that although the curve will still have a vertical asymptote and it is at x is equal to 2, its oblique asymptote is going to have a negative gradient. So it is going to be this way. This is my oblique asymptote, y is equal to ax. So for it to have two turning points, the graph is going to look something like this. And since a is less than 0, that means 4a, we have gotten 2 points, right? That means 4a must be a number that is less than 0, which means that 0 is going to be bigger. So this y coordinate here should be 0. And this y coordinate here should be 4a. That is why the set of values that y can take when a is less than 0 will be when y is less than or equal to 4a or when y is bigger or equal to 0. In part 3, we are analyzing this inequality, and on the left-hand side of this inequality is actually part of curve C. And on the right-hand side, if I were to see this as a graph, this will be from y is equal to ax plus m. What I'm trying to say is that for this particular inequality, since the left-hand side is related to curve C, and on the right-hand side, we can actually represent it by y is equal to ax plus m on a graph. What we are trying to do here is to analyze this inequality, finding the solution using a graphical method. So let's try to do that by first sketching curve C and then sketch this. And we try to synchronize the solution based on our sketch to the solution that is given to us. So for curve C, we are given that a is bigger than 0, b is less than 0. And if you were to look at part 1 again, it is neither this case nor this case, because for curve C to have two stationary points, both a and b must be bigger than 0 or both a and b must be less than 0, and this is not the case, which means that for curve C, we are not expecting any turning points at all. So let me do a quick sketch for curve C, and I'm going to sketch one that has no turning points. The vertical asymptote is going to remain at x is equal to 2. The oblique asymptote, since a is bigger than 0, I'm expecting a positive gradient. So it is going to be a line that is slanted this way. And this is the line y is equal to ax. And since curve C has no turning points, I'm going to sketch curve C like this. So I have this. And the other one is going to be this way. The other part of the graph is going to be this way. So this is curve C, and I'm going to then sketch the line y is equal to ax plus m. Since A is the same as this A, so I'll be expecting this line to be parallel to the oblique asymptote. And if I were to let x be equal to 2, substitute into here, I know for this particular point, it's going to be 2, 2a. So let me just indicate it here. This point is going to be 2, 2a. And if I were to sub 2 into here, we will have a 2a plus m. So we will have a 2a plus m. And since m is a positive number, I'll be expecting this line to be residing above and not below this point. So this line is going to be parallel to this and it's going to be above this point. So I will have a line that is something like this. This will be y is equal to ax plus m. And looking at this inequality, the solution will be when x is less than the x coordinate of this point, or when x is bigger than 2. And if I were to synchronize it to this, when x is less than the x coordinate of this point, or x is bigger than 2, tells us that the x coordinate of this point, because from here we can also see x must be bigger than 2, which means that the x coordinate of this point must be 0. So let's make use of this, where the x coordinate is 0 for this particular point. When x is 0, if I were to substitute into here, I know y is going to be equal to m. So I know the coordinates of this point is actually 0, m. We can actually substitute 0 not just into this, but also this. So let me try to do a bit of working here. So I'm going to say something that is like for curve C, if I were to let x be equal to 0, the y coordinate is going to be a times of 0 plus b over 0 minus 2, which is minus b over 2. And for y is equal to ax plus m, when x is equal to 0, y is going to be equal to m. So from my observation of what I have done here, from observation, I can see that m is going to be equal to minus b over 2.